Welcome everyone to today's NL seminar. Today we have Samee from UC Berkeley, who is a PhD student in CS, and he's working with John DeNero. And he's going to be talking about context for natural language processing. And let's welcome the speaker.
Thank you, Emily, for your introduction. Yes, my name is Samee Ibraheem. I'm a student at UC Berkeley, and today I'll be talking about leveraging context for natural language processing. First, I just want to talk about why I'm interested in context. So let's consider a situation where you're in the office and you've just come upon one of your colleagues that you haven't seen yet today, and you wanted to greet them. So if we thought about maybe an utterance that someone might say in this situation, an example could be, "Hello, how are you?" And there might be some variations on this, but this might be a general sort of representation of what most people would say in this context. However, if we move to the context of a group of friends and you wanted to greet those people, you might instead say something like, "Hey, what's up?" So we might notice that the content of what is said here is similar to the previous situation. And yet, because of this different context, the actual utterance itself might be expressed differently. So here we're seeing an example of context actually affecting what people say. And I think if we think about the differences between these utterances, even though the content is the same, one might not be considered appropriate based on the given situation. Now, if we look at other factors in addition to the situation, we might see things like gender, race, or even occupation affecting how people express themselves in the day-to-day world. So for these reasons, I think it is important for our NLP systems to consider context as well. Now, to give a brief outline of the talk, I'm going to explore first how context can affect our NLP system's accuracy. Then I'm going to talk about an approach to how we can incorporate context into NLP systems. And then finally, I'll be looking at methods for accumulating additional context when that context when the signal might be. So for the first part of the talk, I'll be talking about work that I did during an internship at Google. This is work with Dan Liebling on speech recognition, diversity, in clinical settings. So as a way of introduction, when considering speech and text models in diverse settings, there's been previous work that shows, for example, in English, automatic speech recognition performance may differ based on the specific dialect of English that a speaker is using. So, for example, if you're using a Southern accent, then ASR performance might be different than if you're using a Northeastern accent. In addition, language detection models have been shown to have differing effects on stereotypically Black text. So, for example, if someone is using African American vernacular English, then such text might be misclassified as a language other than English. So these studies have focused on specifically YouTube or Twitter data, but in terms of if we wanted to use ASR systems for real-world tasks, there's actually increasing push in the medical field for physicians to use ASR systems in terms of charting patient history. And so if we think about the effects of differing ASR performance based on race or other effects like this, then we could see that leading to actual health disparities based on patients' differing backgrounds. So for this reason, we thought it was important to consider ASR performance specifically in the medical field. So in terms of doing this, we evaluated speech recognizer performance on a data set of physician-patient conversations. So if we look at the data set itself, we had transcribed doctor-patient conversations, and we tested on about 6,000 utterances of those. And these were in terms of the patients and the physicians, we had their self-reported sex, and for the patients, we also had their race. So for this data set, we focus specifically on male and female utterances for both the patients and physicians. And then for the patients, we focus on white patients versus black patients. Yes.
So it seems like a kind of specifically that the doctor race was not annotated down. Do you know if was there a conscious effort to not do that, or do you have any inkling on whether or not that kind of ablation would matter? Do you think it's mostly? Is there some reason to specifically just focus on patient? I mean, so you're saying you have the sex of both the doctor and the patient, right?
Yes.
But only the race of the patient.
Right. So I don't believe that there was a particular effort to not include the physician race, but so the data set, this was a Google data set. I think just the people who went about getting this data from the hospitals did not have access to that.
Okay.
Yeah. But yeah, so definitely would have been interesting to look at the physicians as well. But yeah, so these were challenging conditions for ASR systems, as it was sort of like far field audio, and there's also natural noise in the background. In terms of the models that we used, so we had two models. The first was a unidirectional speech team model, and this was trained on out-of-domain data, so not the data set that we're dealing with here. And then we also had a medical scribe model, which was trained specifically on this data. In terms of the metric that we used to evaluate these models, we used word error rate, or WERR. And the way that this is calculated is given a reference transcript and the ASR systems transcript, we take the sum of the number of insertions, the number of deletions, and the number of substitutions, and then divide that by the number of words in the reference. So now to look at some of the results. And also this just to make sure everyone is aware. So then lower is a better metric. So now to look at some of the results for race. So again, this is only patients. We have for each grouping the word error rate as well as the ratio of the data set that group makes up. So first looking at the unidirectional speech model, which again was trained on out-of-domain data, we see that the word error rate for Black patients is higher than that of white patients. And if we look at the medical scribe model, which was trained in data, so first we notice that the word error rates are lower, which we would expect as it is trained on the data set itself, but we still see that for Black patients, the word error rate is higher than that of white patients. So this would suggest that we are seeing different ASR performance based on the race of the speakers, in this case, patients. Now, sorry, yeah.
Why is the medical scribe lower? Actually lowers.
Oh, sorry. So the medical scribe model was trained on this data set of doctor-patient conversations, whereas the speech model was trained on
a lot more things.
Or it wasn't trained on this data set at all. So it was trained on just.
Okay.
Yeah.
Oh, so higher means worse.
Yes.
So, oh, okay.
Yes.
Is the parenthesis the distribution of patients?
Yeah. So this means so here we're only considering white and Black patients. There were also groups of other races. So just for these groups, the Black patients make up, for example, for the unidirectional speech model, 14%.
Wait, it's not the same test set?
Yeah. So sorry. Yeah. Between the two, it's slightly different.
Okay.
Yeah.
So these are two completely different test sets also.
Yeah.
For the same pattern.
Yeah.
Sorry, and what's the distribution of the training data? So what percentage of the patients were actually Black? So how much of the data is from Black race utterances?
So for the actual training set, it's about the same. There are other races as well, but yeah, it's still majority white patients.
I assume since you used Google, are you using TensorFlow, Python, and is your data set downloadable from the Google system?
So the data set is not downloadable. So again, this is like medical data. So even as an intern, like getting access to the data was going through like the HIPAA process and all of that. But, yeah, so the data set is not available. But yeah, we this is using like TensorFlow and Python. Yeah, so now moving on to the results for gender. So this is again for the unidirectional speech model, which is trained on out-of-domain data. First, if we look at the patients, so in this case, we actually see that for female patients, the word error rate is much lower than for male patients. And if we look at the proportions, we see that there are more female patients than male patients. If you look at physicians, the trend is in the other direction. So there is a higher word error rate for female physicians versus male physicians, and also fewer female physicians versus male physicians. And then if we look at overall for female versus male, we see a higher word error rate for female.
Do you know much about the way this was set up? I mean, so it seems kind of unusual actually to begin with that Google has a bunch of recordings of doctors talking to patients, and I'm kind of freaked out already. Presumably this was done where everybody knew what was going on, right? Do you know, like, was the microphone like in between or whatever? Because
Yeah, so
this is a pretty big difference.
Yeah, so I was actually going to mention later in some of the analysis, but there is in most of these, it's closer to the physician, so that's definitely would play an effect.
And then I imagine that the physicians tend to kind of say the same thing over and over again, right? Like, again, this is just like an intake, right? Like, how long have you been feeling this way? Do you have any headache? Do you have any nausea? Right? And then like, but the patients say a bunch of different things, or I mean, are the words more diverse from the patients than the physicians?
So I'm also going to show a bit of, I guess, looking at the distributions just of the lengths of, or showing the lengths versus word error rate. And we looked at the distributions of lengths of utterances, and it actually looks like patient utterances are much shorter. But we didn't look specifically at like diversity.
Okay. That's so far the biggest striking thing to me, right?
Yeah.
0.5 or something.
Yeah. So yeah, as you mentioned, looking at patients versus physicians, we see that patients have a much higher word error rate than physicians. And then if we look at for the medical scribe model, here we see some similar trends. So again, because this is trained on the data set, we see that the word error rates are lower for this model. But for female physicians versus male physicians, again, the word error rate is much higher. For overall female versus male, yes.
These are two different test data?
Yes.
Oh, okay. I wonder why do you not compare on the same test data?
So when we were originally doing this, we were looking just at the medical scribe model. And so when we went back to looking at the unidirectional speech model, but yeah.
I see.
Yeah, we should have. But yeah, again, so some of the same trends were looking at patients' word error rates, it's higher than the physician's word error rates. So now to summarize the analysis. So in general, models perform worse on the minority race or gender. So for this case, this is performing worse on Black patients versus white patients, and performing worse on female physicians versus male physicians, depending on the test data on male patients versus female patients. Then we also saw that models perform worse on patient utterances versus physician ones. And this may partially be due to, as you mentioned earlier, that physicians tend to be closer to the microphone than patients in these recordings. But we also noticed that patients tended to have shorter utterances than physicians. So for example, if we looked at female physicians versus female patients, we found that around 34% of female patient utterances contained just a single word versus 16% of female physician utterances. And this is significant because if we look at the distributions of word error rate with sentence length, we see that for shorter utterances, the word error rates are higher. So here we see that this distribution is similar for patients versus physicians. However, these differences likely do not cover all of the disparities that we see in word error rates, as we don't observe such differences between female and male physicians, nor do we see this between Black and white patients. So it's still important to consider other effects that might cause these disparities in word error rates for our ASR system. So in conclusion, we've demonstrated that speaker attributes such as gender and race, as well as role in a conversation, might have an effect on ASR performance. So given that we see, sorry, yes.
Oh, I'm trying to visualize what the neural network would look like. I know a unidirectional model just starts from one input and then branches off to your neural network and then concludes to one output for determining which word, for example, for the word error rate. But what does a medical scribe neural network look like?
This is specific to the medical scribe team at Google. So I guess there's sort of like more like general ASR, like there's an acoustic model, and then also like on top of that, the neural network model. But for that, we don't have like as much specifically for their purposes. Yeah.
Okay, so to improve the neural network, you could use a multi-directional speech. For example, your input would be the word, your output would be the dialect, as you said in the beginning, be able to identify the dialect, and then go through the ASR process and have a higher percentage in identifying the word. Is that something possible?
So you're saying where there are two stages. So first identify the dialect, and then using that information, then produce your ASR transcript.
Right.
Yeah. So I could definitely see that being used for, improving the quality. But yeah, we definitely did not look at those types of models in this study. So now that we've shown that context such as speaker attributes can have an effect on an NLP system's performance, I'd like to move on to looking at ways you might be able to incorporate more context into such a model. So specifically, this is looking at learning an interactive attention policy for neural machine translation. And this is joint work with Nicholas Altieri and John DeNero at Berkeley. So first, what is interactive machine translation? So this consists of combining human and machine translation. So if we look at human translation, usually it is slow and costly, but we expect that human translators are generally accurate in their translation output. Whereas with machine translation, it is usually faster and cheaper, but not as accurate as human translation. So interactive machine translation aims to combine the benefits of both of these. And this can be useful for translating specialized documents such as biomedical data or patents. Now, there are different methods for incorporating the human input to such an interactive machine translation system, which we'll now describe. So first, let's look at an example of translating a Japanese proverb. So the general idea of this translation is earth hardens after the rain. So let's say that we had our machine translation system, which produced a translation, it will rain after the rain. So we can see that it misses some of the words and also repeats some of the words. So then if we had a human translator look at this machine translation output, they could go in and correct the words that they think need to be corrected to produce the final translation, earth hardens after the rain. So this is called post-editing, and consists of, again, the machine translation system producing a translation and then the human edit. So a second option is what we call predictive typing. In this case, the human actually starts their translation. So if we have the same example, the human might type the word earth, and then the system completes the translation. So if the system sees the word earth, then it might be able to get the rest of the translation, hardens after the rain. And then the human could either accept that, or if they think they still need more improvement, continue typing. Now, a third option which we consider is what we're going to call guided attention. In this case, the human is able to click on a word in the source. So if we have the same example, the human could click on the Japanese word for earth, and then the system, we would hope, instead of producing an incorrect translation, would then be able to use this human guidance to correctly translate earth hardens after the rain. So in terms of learning an interactive attention policy, we're having the system be able to take human guidance in the form of an input source word. So there are a couple of challenges here. Training on humans is costly. So what we actually do is we try to simulate the human guidance. And then we also want the system to be able to decide when and where to ask for guidance from the human. So to go about doing that, we use reinforcement learning. So now just to give a brief background on neural machine translation. So given pairs of source and target language sentences, so in this case, an English source and a French target, we have a system with an encoder and decoder that first encodes the source sentence, and then from that hidden representation, will produce the target translation word by word. Now, if we do this with attention, then once we have that hidden representation of the source, we are also able to take a linear combination over the words in the source and use that to then decode into our target. So we're going to be concentrating here on this attention vector that we would use in translating these sentences. So then how do we go about simulating this attention? So in terms of what we expect the human to do in our paradigm, they'll be choosing the word that should give the system the highest probability of correctly translating the next word correctly, the next word in the target. So rather than directly train on humans, we can then take the one-hot attention that corresponds to that word that increases the system's ability to correctly translate the next target word. And so if we then consider a system that always asks for guidance from the human, then we could derive an upper bound on how well such a system should be able to perform with this human guidance. So we then ask, does this actually help a system? The data set that we look at here is the English-German WMT 2016 data set, which has 4.2 million training sentence pairs, and we use 3,000 dev sentence pairs. And then we apply BP with 32,000 mergers. In terms of the model that we use the Google sequence-to-sequence model. In the encoder, hidden units are size 512, and we also have decoder GRU units 512 and attention 512. So while a baseline model attained a BLEU score of 19.37, when we always ask for guidance from a human or a simulated human, we were able to achieve a BLEU score of 32.51.
Where do you get the guidance from?
Sorry. So we are simulating the guidance by taking the attention vector and replacing it with the one-hot attention that maximizes the probability of the correct target word.
How do you know the correct target word for a particular?
So during training, we have the reference translation.
Yes, we don't have the word to word. You don't have the information about what word translates.
Right. So what we're doing is at each step, we are taking the correct word in the reference translation.
Which word? Oh, sorry, the correct word, the reference translation. Sure,
Yes.
I get that, right?
And then we are going over. So we also have all the words in the source sentence. So we go over the words in the source sentence. We take the one-hot attention that would correspond to that word.
Okay, with that word. So
In the source sentence.
yes, you don't know which word is the translation of the word you're producing in the target sentence unless you have some other. Right? You don't have. You only have sentence alignment. You don't have.
Yeah, we don't have word alignment.
So
What we're doing is we're going over all of the source sentence words. We're taking the one-hot attention for each of those.
and you're doing whichever one gives you
Yes.
the lowest loss.
Yeah.
Okay. Got it.
So doing this with 100% guidance allows us to then improve the BLEU score. So now, if we always ask for guidance from the human, that would be costly. So we then look at reinforcement learning. So the reason,
So from what you described in the previous slides, it seems like the whole procedure, you don't need to ask for human guidance at all, right? So there isn't any additional resource. It's like this transition is a little unclear to me.
Mhm.
Because the motivation is to say if you always ask for human guidance, it will be costly. But from the previous slides, it seems you don't need additional human guidance at all. So it's like it all comes for free. It's more of a hard attention trick on the sequence to sequence model. So I think I probably missed something here, but this transition is a little confusing.
I think because it's important at the test time, because at the test time you need the human. So that's the method that they had is okay for training because they have the correct target word. But at the test time, they can't use their stimulated method. They actually need the human to point to the word.
Actually, that makes me wonder, what do you do at test time?
Yeah, exactly.
right. So at test time, then we use, right. So at test time,
To get the number that you reported on the last slide, at 32. You can't just cycle and take the argmax now, right?
oh, right. So now what we're doing is we have the system that is trained with, So for this number, we haven't trained a system with reinforcement learning. So yeah, this is at every time. We're just saying if we ask at every time step.
No.
Yeah.
So during inference, right?
Yes.
Now you've got your hidden vector, right? And you're gonna take a hard attention lookup of the source word, right? And you're gonna produce a target word, but you can't do what you're doing during training, which is, so how do you decide which word that you're gonna attend to?
So at this point, then we're just taking, we're just, so at this point, we're just, still taking, because we still have for the test set, the reference.
Oh, I see. Let me guess whether this is what's going on. So during the test time, you take the correct translation. You basically pick the answer and you use that to decide your attention.
Mhm.
And you use that to do the translation and evaluate on that.
So using the correct word, well, no, this can't be right.
Basically,
This wouldn't work.
they take the gold translation of the test data. So they already have the correct.
And use that to pick which word you use, and then actually you do whatever the model says. Because if you did
Use
that, you
that
get 100.
No. They just use that to decide the attention, but that attention could still be wrong.
Is that what you're doing?
Like
Yeah, so,
during
sorry.
tests, are you also doing the argmax with all the attention vectors?
Yeah.
Like okay, so you're.
But then you're going to totally go off the rails, right? So like you start translating in like a different direction. Is your gold is your reference just always like the third word, for example, right?
Mhm.
Like the third word in the reference may have nothing to do with what the third word should be after you start translating, right? Because like what was the example from the Reed's talk yesterday? Where it's like, I don't like this, and if you start saying, you say I do not like this, then now you shouldn't try to predict like for the third word once you produced I do, right? Because that would get you I do like this.
Yeah.
But that is what you do?
Yeah.
Okay.
So we're not.
Which is why you
don't
make it
exactly
100. But,
yeah. Yes.
Okay. So there is still, you can call it cheating or guidance.
Yeah. So,
Okay,
but
got
you
it.
take.
So now we're going to discuss how we then train a system with reinforcement learning. And since decisions that we make about the translation of the next target word might not only affect the current word, but also words down the line, then it is important to consider a method of training that allows us to take. So in order to do that, we use policy gradient. So in terms of the states that our agent, which is the translation system, can be in, we consider the network activation before generating the next target word. In terms of the actions, here we have only two: either ask for guidance from a human, or a simulated human in our case, or proceed without that guidance. In terms of the transition function, then, in the case where we ask for guidance, we would replace the system attention with the one-hot attention vector that corresponds to that word. Otherwise, we would keep the system attention as is.
Which is a soft attention.
Yeah. In terms of the words, we use the cross-entropy sequence. And then our policy gives us a probability for requesting. So in terms of the objective that we're trying to optimize, we want to maximize the expectation over discounted future, the sum of discounted future words. For our discount factor, we use 0.99. And then for our value function, at each state, we want to estimate the value of that state. So again, the expectation of discounted future rewards.
I'm sorry, I missed this. What's the reward function? What's our?
Oh, sorry. So for here, it's just the cross sequence.
Which is the cross entropy of the rest of it.
And then for our value function and policy function, we are parameterizing that with neural network. And the input for the value function is the standard decoder input. And for the policy function, in addition to that, we also give it the input to the softmax layer.
With guidance, potentially? Policy going the rest of the way? I'm just trying to think of how this plays out.
So, yeah, potentially. So I guess in terms of this policy network, this is giving us whether we're probably.
You're loading a policy network, so you just get a score.
Yeah. And then we also, again, want to have a system that is able to decide when to ask for guidance, because we would expect that if it could always ask for guidance, it would just always request it. So in order to do that, we add frequency, action frequency regularization. because there's a threshold on the amount of times that the system can ask for guidance. So in terms of the results, so we compare our trained system to a system in which the policy network is randomly initialized. And we find that our reinforcement learning model is able to consistently outperform this random model. So here we have a plot of blue versus this, again, is like the threshold that we give on asking for human guidance. So if we had 1, that would mean always asking for guidance, and 0 means never asking. So we see that our model, for example, if we are able to ask for guidance half of the time, then our model is able to do about 2 blue points over a randomly initialized model, and 8 blue points over the baseline model that never asked. So here we have presented an approach for allowing a trade-off between translation quality and the effort required of human translators in an interactive machine translation system. And this method allows for adding an additional type of context, specifically here, the human guidance, to be incorporated into a neural machine translation system. So next, I would like to look at how we can accumulate additional context when that context might be limited. So this work is gender detection from text when the signal is sparse, which is work with John DeNero, again at Berkeley. So as a way of introduction, when we think about grammatical gender, which is available for some languages, lexical items such as first-person pronouns or adjectives can give an indication of a speaker or writer's gender. In contrast to this, if we look at languages such as English, whereas certain phrases might indicate the gender of a speaker, some of the time, like maternity or paternity leave, for the vast majority of utterances, a speaker does not explicitly indicate their gender. So in terms of previous work in this area, usually work has been on in terms of improving the features that are used to classify gender. However, these studies don't explicitly look at methods for how to improve gender classification when the signal is sparse. So for our study, we look at whether aggregating over speaker utterances can actually improve the gender classification results. For our data set, we use the blog's authorship corpus. So this is a corpus of English blogs in which the gender of the blogger is indicated. We have about 86,000 training utterances and 1,400 test utterances. And then in terms of the models, so for our baseline, we use a transformer encoder tiny model. This has 2 layers, 128 hidden units, and 1,024 batch size. And then on top of that, we also investigate 4 methods of aggregation over speaker utterances. So first, let's look at our first aggregation method, aggregating over the lines. So here, what we do is we combine the utterances produced by a single speaker. And since it's impractical to train a model on the fully concatenated utterances, as a lot of these blogs are long, we do that up to 128 tokens. And then the baseline model in this case remains the same. For our second method, we aggregate over labels. So here we take the mode over labels predicted by the model for a particular speaker. So for example, if the majority of a speaker's utterances are labeled as female, then we take that to be the predicted label. And for those utterances that are labeled as male, we relabel them as female. And again, in this case, the baseline model remains the same. This is just a post-processing step. For our third method, we aggregate over the logits. So here, what we do is, given an ID for each speaker and a set of the speaker's utterances in a batch, we take the log probabilities for each utterance and sum those over all of the speaker's utterances, and then divide by the number of utterances. And then for our fourth method, we aggregate over encoder outputs. So in this case, given again a speaker ID and their set of utterances, we take the sum of all the encoder outputs for that speaker's utterances and then divide by the number of utterances. So if we look now at the results, so for the baseline model, we get an accuracy of 53.8%. And since this is a gender balanced data set, this is not much more than the 50% that we'd expect. Whereas if we aggregate over the lines of a speaker, then we're able to improve to 60%. And if we do that aggregation over the labels, then we get 65.9%. Aggregating over the logits gets about the same with 65.1%. And finally, if we aggregate over the outputs, we're able to see the biggest improvement to 75.7%. So this would indicate that aggregating information over speaker utterances allows for increased gender classification accuracy, and that the method of aggregation is also.
Sorry, can you go, what's, I think I missed it. What's the difference between aggregating over labels versus outputs?
So aggregating over labels is just taking the mode over. So we have our baseline model. Then that model will produce just like the set of labels for each utterance.
53.8%, correct, yeah.
And then what we do is for each speaker, we look at the majority that was labeled for those utterances.
And then what's outputs?
Oh, so this is aggregating over the encoder outputs. So averaging over.
Okay, got it. It's a bit of a argumentative question, but where do you see the application of this technique?
Right. So I guess one application that I would see is for example, if you wanted to look at machine translation from a language like English, as you mentioned, which is not as gendered or explicitly gendered, to a language that is more gendered, where it is important to translate correctly to know the gender of the speaker, then we would hopefully want a model that is able to, even though we have this non-explicitly gendered model, be able to aggregate whatever sparse signal is available and use that to correctly predict the gender and thus translate correctly. So here we have introduced approaches for improving gender classification through aggregating over speaker utterances. And hopefully, yeah, this could allow for these results to be used as additional context for downstream tasks, such as machine translation. So as a general conclusion, we have looked at how context can play a significant role in natural language processing systems performance. We've shown that incorporating context into such systems can improve their translation quality, and we have suggested approaches for accumulating information or additional contextual information when that information is sparse. So with that, I would like to conclude.
Any questions?
If you go back to the machine translation section, middle part, I was wondering if There's kind of a common maxim that if there's a way to avoid reinforcement learning, you should. And I wondered if it was needed in this approach. Like, I could imagine that you could have your output distribution be like your vocabulary plus like ask for help, right? And then like have that be one of the choices where you put in, but you put in a loss penalizing term there, right? So that would kind of like directly get at the same information that you're putting in. Whereas, I mean, I know that you're, well, by doing the RL part, you're modeling when you need to ask for help. But I guess I don't know if you tried that kind of thing, or if you have some analysis of the policy that gets learned that gives you an indication that it really is learning, like to ask when it becomes tricky or anything like that. Is there any kind of insight you can give in that area?
So in terms of I guess how you would then incorporate, well, I guess, yeah. So we did look at just the amount of time that I was asking for help. So it is similar to the threshold that we are using as the penalization term.
Mm-hmm.
In terms of, I guess, when we use such a system versus, we did do a preliminary study of looking at human provided guidance. So there definitely is disparity between if we had a human provide guidance versus the simulated attention. But we do see that the distribution of difference between the human versus simulated does center around 0.
Sure, I have no problem with the fact that you're doing a good job modeling what a human would do. I'm just talking about I mean, when you're doing the reinforcement learning, you have to learn your policy model too. So it probably takes a lot longer to train it, right, than you would training a baseline model. Whereas instead, you could have you extend your output table by one column, where that extra column is the ask for help column, and when you predict that, then you go and attend to the max, and then do your prediction from there. Like, that's just a different way of reformulating the problem, that it doesn't actually require you to learn a policy now. But you still have the same knob. It's just a kind of like more of a big hammer. And I just wonder if, so a reason not to do that would be like that you get a totally non-representational of reality approach. And but the advantage would be it would train a lot faster.
Yeah, so we haven't looked into a method like that, but yeah, it would be interesting to see how that did.
Any other questions? All right, so if you have additional questions, you can talk to the speaker after. Otherwise, let's thank our speaker again.
Thank you for having me. Thank you, Emily, for inviting me here.